Hello everyone, my name is Yuhuang Hu. I'm from the Institute of Neuroinformatics, University of Zurich and ETH Zurich. Today I'm presenting our paper, Learning to Exploit Multiple Vision Modalities by Using Grafted Networks on behalf of our co-authors Toby Delbruck and Shishi Liu. This work is supported by the NCCR Robotics. In recent years, there are types of novel sensors, such as event cameras, hyperspectral cameras, thermal cameras, and polarization cameras. These cameras supply unconventional visual outputs such as polarity events, hyperspectral data cube, thermal frames, and polarization imaging. To process these novel visual outputs using deep learning algorithms, there are a few ways. The first way is to follow supervised DL training. However, the problem is the lack of large labeled datasets. By the year 2020, there are more than 92% intensity frame datasets. For other visual modalities, there are only less than 8%. The second way is to first compute pixel-level information before processing by a DNN. For example, we can reconstruct intensity frames using polarity events. This reconstruction introduces additional latencies that are not desirable for certain scenarios. To resolve these problems, in this paper, we propose network grafting algorithm, or its short form NGA. Given a pre-trained network that detects objects in this case, NGA trains a grafted front end to replace the original front end. The grafted network can directly process the input from a novel sensor and achieve competitive performance. Now, let's look at how NGA works exactly. We first divide a pre-trained network into three parts: a front end, a middle net, and remaining layers. The input image is first mapped to a set of front-end features H and then transformed into middle net features R. Finally, the remaining layers outputs the prediction of the objects. A grafted network only trains a grafted front end. The grafted front end features H hat is then transformed into R hat by using the same middle net as in the pre-trained network. The same set of remaining layers is also responsible for predicting objects in the grafted network. The training optimized a three-part loss. The first loss is called feature reconstruction loss that maximizes the similarity between H and H hat. The second loss is called feature evaluation loss. It maximizes the similarity between R and R hat. The third loss is the feature style loss. It aims to let H hat and R hat to have image feature style as done in image style transfer. Because NGA only operates on the feature level, so the algorithm is self-supervised and does not need any label. It only needs a small set of synchronized intensity images and novel camera inputs, typically a few thousand pairs. Our experiment setup for object detection is based on YOLO V3. On the right, we show 6 front-end and middle net configurations used in this paper. S1, S2, and S3 are the choices of a front end. S4 and S5 are the choices of a middle net. For this presentation, we use this example. Specifically, the first 3 residual blocks as the front ends and the next 2 residual blocks as the middle nets. We tested NGA on 2 datasets. For thermal camera modality, we use FLIR thermal dataset. And for event camera modality, we used MV-SEC-Day2 recording. The pre-trained network predictions are labeled in red. And the grafted network predictions are labeled in blue. We can see in the most cases the grafted network can detect as many objects as for the pre-trained network. Specifically, when the scene is dark and noisy, the grafted network can detect more objects than the pre-trained network. In terms of the performance, the grafted network detection precision improves 50% compared to the pre-trained network. This is largely due to the night scene in the thermal dataset. In addition, the grafted network only trains as low as 5% parameters compared to the pre-trained network. The second experiment is car detection with the event camera dataset. The red bounding box are cars detected by the pre-trained network. and the blue bounding boxes are predicted by the grafted network. We can see that the detection performance of the grafted network and the pre-trained networks are close together. Furthermore, when we combine the prediction of two networks together, the detection score improves. This indicates that the grafted networks can detect some cars that are hard to be captured by the pre-trained network. Similar to the previous slides, the GN only trains 3 million parameters compared to the 62 millions of the pre-trained networks. We have shown the use of NGA for detection. We would like to understand the question, where is the evidence whether grafted features are informative? To answer this question, we first extract the grafted front-end features. Then, we optimize a randomly initialized image using the pre-trained front-end. The optimization target is to find a decoded frame that closely represents the grafted features. This slide shows two decoding examples. The first row is a thermal dataset example. The intensity frame on the left is captured at night, and we barely see any objects. The thermal frame in the middle represents the scene well, and we can see objects such as cars and trees. On the right, the frame that is decoded from the grafted front-end features captures the scene very well. We can clearly see cars, trees, and sky that are seen in the thermal frame. The second row is an example from an event dataset. The intensity image on the left has motion blurred car. The motion blur is reduced in the events, and we can clearly see this car in the decoded frame as well. In conclusion, this study shows that a grafted features often faithfully represent the input scene. To sum up, first, NGA does not need a labeled thermal or event dataset for training. This is particularly useful when there is no labeled data for the target novel sensor. Second, the newly trained GN processes the thermal or event data directly. Finally, NGA also saves us precious training time. In addition, we would like to show you a bonus video where we graft a multi-person 2D post-estimation network. Enjoy. Thanks for your attention, and we hope to see you at the conference.